And so what was originally atoms that were nicely symmetric, like that, will now get distorted so that the positive charges and the negative charges will have different centers. Will have different centers so that you'll have a situation like this. And so on. So the atoms in the material will get distorted. And that means that each atom will become effectively a dipole, in that it's a material where the total charge is 0. Remember, that was our dipole, a minus charge, a plus charge, but separated by some distance. So that what you would have is that this would be the distance L from there to there. And you would have little dipoles for each atom given by Q times L. So the question is, what will be the effective charge that's produced by that arrangement? Now, when you had a conductor, what happened was L became the width of the conductor. The charge is separated so that you ended up with not just a distorted atom, but the electrons actually moving to one side. And then what happened is you produced a field then that pushed back the other way until it could exactly cancel the field you were applying, so that you got no field inside the conductor. Now, in this situation, that's not going to happen. But what is going to happen is we'll have dipoles throughout this region. So, what we want to ask is, what is the effective charge that is produced by this? Now, if the dipoles were the same all the way across, everywhere inside, the plus and minuses would cancel, and there would be no effective charge. But at the surface, there'd be nothing over here to cancel it. And so the effect would be that you would get a positive charge here and a negative charge there, and nothing in between. Now, if the polarization, the amount the atoms were stretched, was different at one point in here than at another point, then you would get a charge in the middle as well. So let's see if we can figure out what those two things are. Now, in order to do this, we're going to define a polarization, which we'll denote by capital P, which is the dipole moment per volume. So the polarization is going to be the dipole moment per volume. Okay? So now, let's look at two neighboring regions in the material. So here's a little chunk, and we're going to, if the polarization is going to be continuous, then let's just line up our chunks for the moment such that the polarization is directed in this direction. Let's call that the x direction. We can do the same thing for y and z, but just look in the x direction for a moment. And consider two boxes here. One located at x and one located at x plus dx. Okay? Now, what will be the total charge? Let's suppose this cross-sectional area is A. That's the cross-sectional area of the thing. Then, what is the total dipole, electric dipole in this box? Well, the dipole in the box, little p, it's in the x direction just because of the way we drew this. And it will be the polarization, which is the dipole moment per volume, evaluated at x. This This is P in the x direction. So we'll call that just px. Times the volume of the box, which is A times dx. So that will be the dipole moment in this box. Now the dipole moment in this box of x plus dx is, so I'm going to just do the x direction, so I'm going to forget the vectors for the moment, will be P of x plus dx times a dx. Okay? Now, the dipole is the charge times the separation of the charges. And so you get a minus q here, a q here, and this distance is dx. And so the charge that is occurring on this face is equal to the dipole in this region. Right? The charge that is occurring here due to the dipole in this box is going to be a positive charge, and it is going to be the dipole in that box. And so it is the dipole. See, we got P is equal to Q times dx. That's the dipole moment in here. But that is P of x a dx, that's the dipole, times dx. Because the little p of x was the capital P of x times a dx. So this is a positive charge on this face, but there's a negative charge on this face due to the charge, the dipole moment in that box. So everybody following okay? Yeah, there's a lot of P's, and they're hard to distinguish them. Okay, so let's change our notation a little bit. Let's let S be the dipole moment instead of little p, and that'll make make it clearer. So that means that S in box X is that, and S in box S plus dx is that. Okay? Then S is equal to Q times dx. And that is then this thing. And so that means that Q associated with this box on this face is P of x a dx. Just dividing both sides by dx. So this is the Q, positive Q at this face due to the dipole moment in this one. But there's a negative Q on this face due to the dipole moment in this one. So Q net is P of x a dx minus P of x plus dx a dx.
So is S now the dipole moment for volume?
S is the dipole moment in this box. The dipole moment in this box is the polarization in this box times the volume of the box. And the polarization in the box is P of x. The volume in the box is A dx. And so the dipole moment in this box is that much. So you then will get a charge on the face of this box, which is, since the dipole moment was the charge, which is the charge on this face or the charge on this face, times the separation. The dipole moment was the charge on this face times the dx, because the dx is the length of the dipole. And that means then you're getting a positive charge buildup on this face because of the polarization in this box, and you're getting a negative charge on this face because of the polarization in this box. So the net charge on that face is what you got from this box minus what you got from that box. And what you got from this box, because of what we had here, which was the q dx, that was the dipole, was what we had here, P of x times A dx. Okay with everybody? So the net then is we had this thing divided by dx, and so the charge was this thing. P of x times A was the net charge, and so we had this. And so the charge density associated with this is the charge, which is P of x minus P of x plus dx times the area divided by the volume of the box, which is A times dx. And the A's will cancel out, and the charge density then is minus the derivative of P with respect to x. Now, exactly the same thing would have happened if we looked in the y direction and we looked in the z direction. But the divergence of P is the partial of px with respect to x plus the partial of py with respect to y plus the partial of pz with respect to z. But that's exactly what we've got here. This is just the x part of it. Then we'd add the y part and the z part. And that means that the charge density produced by this polarization is minus the divergence of P. That clear to everybody? I mean, this is now not arithmetic. This is the physical idea. Point being, if the polarization varies from point to point, that means the charges at one face will not cancel the charges in the next box, and you will get a net charge. If the polarization is uniform from place to place, then they'll cancel everywhere across the box, as I drew in the picture up there. All right? So in the interior of the box, it's going to look like this. What's going to happen at the surface of the box? Well, so here's this dielectric. And right at the surface, we have dipoles. putting a positive charge there. And how big a charge will there be? Well, it'll be coming from the box right next to the surface, where you have minus Q, Q, and the size of that Q on this face is simply what you had here, P of x times A. And so Q is P at the surface times the area, and therefore the charge per area at the surface will simply be the polarization. And it will be the polarization that is perpendicular to the surface. Because if the polarization were this way, you'd have no variation in charge on this side. The charge variation would be here, plus to minus. And so the result is you get a surface charge density, which is P dot n, where n is the perpendicular to the surface. Okay to everybody? So two effects occur. In the volume, if you have a divergence of the polarization, you get a charge. On the surface, if you have any polarization, you get a charge, provided it's perpendicular to there's a component perpendicular to the surface. Is it okay? Everybody's all right with this? Okay. So now, let's see how we need to change the equations we started out with to allow for this. Well, that's easy to do. We know Maxwell's equation, the first Maxwell equation, which is the divergence of E is equal to rho over epsilon 0. And that's true. It doesn't matter how we arrange the charges. You get a charge, it produces an electric field. Okay? But now, what we've discovered is that there will be an effective charge produced by this polarization even if there were not any free charges here. I'm going to put a little F here to mean these are the normal charges that are free to move around in the material. In addition to those, there is a charge, effective charge, due to a polarization. See, dipoles have no net charge on them, but they have the effect of a charge if there is a divergence in the polarization. So that what I do is I replace rho free by rho free minus the divergence of P. So that allows for the effect due to the atoms displacing, even though there's no net charge. Now, I could have accomplished exactly the same thing by not doing any of this and adding up the charge on each piece of the atom, the nucleus and the electrons. And then I wouldn't have had to do anything about that. I've gotten rid of my dielectric. I'm just looking at each individual atom in the thing. That would be just fine. This is a subtle business now. We're going to be sure we understand this. So I'm saying I have two options. One, I can go to every single charge that exists. And I can write divergence of E is rho over epsilon 0, and I will be fine. That is the ultimate way to do it. I, on the other hand, is going to make life a little simpler for me. I'm going to make an approximation. And the approximation I'm going to make is, well, those charges that are bound on the atoms, they cancel each other out almost. The almost is they make a little dipole. And because they are not exactly together, they don't perfectly cancel each other out. I'm not going to add up each charge. I'm going to add up each atom. And so I'm going to replace the atom. Instead of adding up two charges, I'm going to replace it by a little dipole, and I'm going to add up the effect of the dipoles. See what we're doing? So ultimately, add each charge. Cheat. Say, okay, I'm too lazy to do that. I don't want to figure out all these. I mean, God, if it's uranium, there are 92 electrons in here and 92 protons. I don't want to add up all that stuff. I'll use the fact that, to a pretty good approximation, they're just a little point dipole. And I'll add those up. That's what we're doing. If we wanted to do better, we would replace the atom by no net charge, a dipole, a quadrupole, an octopole, hexadecipole, some ridiculous order of these things. What do I mean by that? When I wrote down the dipole as these two charges, I took the limit that it went to 0, the spacing between them, and made the charge as infinite. That's not the real world. The real world, there is a finite, very small, but finite distance between them. And so when I do this approximation, remember I did that calculation to find the dipole moment. I took QL goes to 0. That was a constant as L went to 0. I should keep all of the rest of the terms in that power series. And those would give the successive higher order approximations. It's just that the spacing between the electron and the nucleus in an atom is very small compared to any macroscopic distances. So to a pretty good approximation, you can replace it by just a dipole. Everyone understand what we're talking about? Okay, so that's what we're doing. So we're now splitting things into net charges, actual free charges, and the bound charges, which are being replaced with dipoles. Okay, so this is equal to the divergence of E. Now, it is convenient to rewrite this a little bit. Let's multiply both sides by epsilon 0. And so you get rho f minus the divergence of P. Epsilon 0 is a constant, so I can put it inside the del sign because it's a constant. Okay? Now I'm going to move that over to here. And I'll have rho f is equal to the divergence of epsilon 0 E plus P. Okay? So now I'm going to define a new quantity, which I call the electric displacement D, which is epsilon 0 E plus the polarization P. And then the first Maxwell equation becomes the divergence of D is equal to rho free. So now I've got a quantity whose divergence is produced only by the free charges. I don't have to worry about the polarization charges in the divergence equation. Well, that just looks like just symbols. I mean, I didn't really do anything. But now I'm going to make a physical assumption. Yes?
Rho is the charges.
Rho is the free charges that are not bound in atoms.
So it's not the QL, or it is?
No, it is the things that aren't the QL. The divergence, the minus divergence of P is the charges that came from the dipoles. This is the charges that comes from real, honest-to-God charges, not just point dipoles. Now we do some physics. And that is, why did we get a dipole moment in the first place, a polarization in the first place? Because we applied an electric field to it. If the electric field isn't too big, we would expect the polarization to be proportional to the electric field. If the field gets very big, then you'd expect it won't be strictly proportional. You'll start getting quadratic terms and so on. But as long as the electric field isn't too large, you'd expect the polarization to be proportional to the electric field. And so this is called the linear dielectrics. And almost all of them are for any reasonable field. For linear dielectrics, we now make the physical assumption that the polarization is proportional to the electric field. Now it's even possible to have exotic materials where you apply an electric field this way, you get a polarization that isn't quite in line with it. We're not going to worry about those. We could deal with that. How would we do it? Chi-e wouldn't be a constant, it would be a matrix. It would be a tensor. But we're not, you'll be happy to hear, we are not going to do that. Ours are going to be the nice, simple situation, which is true 99% of the time, where the polarization is just proportional to the electric field in the same direction.
There's a common material there. You don't see anybody with like those polarizing glasses, but or electric glasses, but polarizing lenses are a common example.
So they're real and they're important, but life is hard enough. And you'll be happy to know even I have some limits as to what I'm willing to put you through. So we are not going to do that. It's an easy thing to do, but we're not going to do it. So let's put that in here. And now what we get is that the divergence of E, well, let's put it this way. What we've got over there is D is equal to epsilon 0 E plus chi sub E times E. Or in other words, epsilon 0 plus chi sub E times the electric field E. Now, that's just a constant. I'm going to define that constant to be kappa epsilon 0 E, where this is called the dielectric constant. So this just says that kappa epsilon 0 is epsilon 0 plus chi sub E, and therefore kappa is 1 plus chi sub E over epsilon 0. We're never going to worry about that. This is the form that matters. So now our equation becomes the divergence of, for D, kappa epsilon 0 E is equal to rho free. What was the second equation? The curl of E was equal to 0. Electricity is still a conservative force, so the curl of E is equal to 0.
What is epsilon 0?
K was 1 over 4 pi epsilon 0. It was just a choice of which form you wanted to write. The K in Coulomb's law is 1 over 4 pi epsilon 0. It's just a definition of a different constant. In other words, Coulomb's law we wrote as k q squared over r squared. You could also write it as q squared over 4 pi epsilon 0 r squared. It's just a choice of which you want to use. Generally, I use k because that's a simple number, 9 times 10 to the 9th. Epsilon 0 is not so simple. It's like 8.8 something, 10 to the minus 11.
So it's a constant.
Yeah, it's just a constant. In other words, epsilon 0 is k over 4 pi. I mean, epsilon 0 is 1 over 4 pi k. The reason for using epsilon 0 is that it makes this equation divergence of E was equal originally to 4 pi k rho. And so by letting that be 1 over epsilon 0, the equation looks simpler. And that's why you often see it done in terms of epsilon 0. Gets rid of the 4 pi's. Now you see there's a problem here. There are two situations. Let us suppose that kappa epsilon 0 is a constant. If kappa epsilon 0 is a constant, then the first equation becomes kappa epsilon 0 divergence of E is equal to rho, implies that the divergence of E is just equal to rho over kappa epsilon 0. So the electric field is just reduced by a factor of kappa. And that is the case in a large number of circumstances. But suppose kappa isn't a constant. Then the divergence of a scalar times a vector is the gradient of the scalar dotted in the vector plus the scalar times the divergence of the vector. And if the gradient of that is not 0, this is not true. Now, most materials have the same value of the dielectric constant everywhere in the material. So inside the material, that gradient is 0, and this is fine. But it's obviously not 0 at the boundary. You went from kappa on the inside to 1 on the outside. So obviously, the gradient of kappa is never 0 at the boundary. So you have to be a little bit careful. It's fine to use all this stuff as long as you are aware that kappa doesn't have to be a constant. Making sense to everybody? All right. So now, let's apply this idea to solve some simple problems. Unlike the arithmetic we've been doing the last few days, this is the physics. So it's really important we understand the ideas here. Is everybody clear on those? What we've done is we've chosen to split the total charge in the universe into two pieces. That due to charges that are free to move around, and that due to atoms, where the charges are stuck on the atoms. And we have replaced the atoms by dipoles, saying that, well, the spacing between the positive charges and the negative charge is very small on a macroscopic scale. So we ought to be able to replace it with dipoles. The net charge on it is 0, because there's the same number of electrons and protons. But they can be distorted a little bit, which will make little dipoles. So physically, we're saying, okay, the electric field is going to be due to these two things, charges and dipoles. We've thrown away the atoms, which means we've thrown away the dielectric. and replaced it with a collection of point dipoles. Sensible to everybody? That's all that went on here physically. Yes?
So a dielectric is an accumulation of dipoles?
Right,
Is that correct?
precisely. And a nice uniform dielectric would have the same dipole everywhere in the material. And the result would be there'd be no effective net charge except at the surfaces. Okay, so we're feeling all right with this?
So how is that different than the electrons themselves moving?
Okay, the difference is when things get done, the atoms are still, what's happened is the charges have moved to the sides so as to completely cancel the field inside. No field inside, no distortion of the atoms inside, therefore no dipoles inside, and all you have is the charges on the surfaces. And that's what happened with an electric field in a conductor. In a dielectric, they can't do that. And so what happens instead of them moving over here, they distort and you make a whole collection of dipoles inside. Is that right? Okay. So, now let's see if we can apply this idea to interesting physical situations. So let's do about the simplest geometry we can imagine. We've got a block of dielectric. And here with some dielectric constant kappa. And then we place it between two large conductors. You know, the usual infinite conductors. So everything is nice planar geometry. Now, let's put a charge plus Q on this one, minus Q on that one. And let the area of these things be essentially infinite area A. We'll put no charge on this. It's just a block of dielectric. Okay? Now, this is a conductor, so where's that charge going to be? On the surface of the conductor, right? So we got a charge Q on this face. Let me now draw a little imaginary box here and extend it arbitrarily far until I get over anywhere up to but not including this conductor. Okay? Now, did I make any approximations when I defined the divergence of D was equal to rho? No. I didn't make any approximations there, except the fact that I was going to assume it was the divergence of P gave us the charge, the effective charge. And that was simply the approximation. I can use dipoles and not higher order terms. But no assumptions about it being constant throughout or anything like that. So I can then use the divergence theorem, and I will get the integral of d dot dA will equal what's on the right-hand side. So it will simply be equal to the charge inside. Okay with everybody? Now, by the symmetry of this thing, D will be pointing from here to there. So D will point like that. Let's draw my box the other way. Let's make it go into here. So there's my box, extending just short of that conductor. All right? Now, in here, this is a conductor. Since the electric field is 0 in the conductor, D is 0 in the conductor. There's a total charge on this face of Q. The D only comes out over here. So this will be D times A is equal to Q. And therefore, D is equal to Q divided by A. All right? Now, as I go over this way, do I encounter any free charges? No. So all the way across this thing, D is exactly the same. D is Q over A everywhere. So we get D is Q over A times, and let's make this the x direction. So it's dQ over A times x hat. All right? Now, what is the electric field in these various regions? Well, in this region, I have a vacuum. I have kappa equal to 1. In this region, I have kappa equal to 1. And so, let's label these now. This is region 1, this is 2, this is 3, this is 4, and this is 5. So, in region 1, the electric field, of course, is 0 because it's inside the conductor. In region 2, the electric field is E. In here, with our linear dielectric, the relationship is D is kappa epsilon 0 E. Kappa is 1. So E is equal to D over epsilon 0.
Why would kappa equal 1 in a vacuum?
Because kappa came about from this. The polarization in here is chi e is 0 because it's just air. Remember, the polarization was chi e times E. There's nothing to polarize, so chi e is 0. And that makes kappa equal to 1. So, this is D divided by epsilon 0, which is Q over A epsilon 0, or sigma over epsilon 0. All right, region 3. Well, now, D is kappa epsilon 0 times E, and therefore I get sigma over kappa epsilon 0. Just a moment. Hello? Yes. Okay, I'll be down. I'm in class now, so I can't talk, but I'll be down. Thank you. Okay. Region 4. I'm back in the air again. And so in this region, I will get E, and these are all x hat. And here I'm back in the air again. So I get sigma over epsilon 0 x hat. And in region 5, I'm back in the conductor, so I get 0. So the effect of the dielectric was just to reduce the electric field by a factor of kappa inside that thing. And that is normally what happens. Normally, the only effect of a dielectric constant is to reduce the electric field by a factor kappa. Suppose that had been a conductor in there. What would the electric field in it have been? Zero, right? Because it's inside a conductor. In order to do that, what would I have done to kappa in this equation? Let it be infinite. In other words, if you solve a problem for a dielectric, and you want to look at what would happen with a conductor instead, just let the dielectric constant go to infinity, and that forces the electric field to be zero, and you get a conductor. Physically, what it says is that since the electric field is to be zero inside a conductor, that means that the system is perfectly successful at polarizing as much as it wants to do, and that means you have to make kappa E, that chi sub E, very, very large, and that in turn makes the dielectric constant very, very large. In this sense, a dielectric is just a frustrated conductor, one that wasn't quite able to do what it wanted to do. Okay, making sense? All right, now, to solve more complicated problems, we need to look at the boundary conditions a little bit. And so, I want to look at the boundary conditions on E and D at a surface. So here's some surface between two materials, region 1 and region 2. And in general, you could have some charge on that surface. You probably won't, but you could have. So, I want to apply the divergence theorem, which says the integral of d dot dA is equal to the charge enclosed in the box, to determine what the boundary conditions on D are at an interface. So, I will have D in this region, call it D2, and I'll have D in this region, call it D1. Now, any surface, if I take a small enough area, is going to look like a plane. Okay? So, if I want to calculate d dot dA, I make this surface very, very small. d dot dA, dA is this way. d dot dA then gives you the component of D perpendicular to the surface. Right? You dot this into this, you get the component D perpendicular to the surface. That's the normal component. So, when I do this, I get D2 normal on this side. On this side, I get D1 normal, but it's pointed into the box, so it's minus. And that has to equal the charge divided by the area. And so we say that at a boundary between two materials, D2 normal minus D1 normal is equal to the charge density on the surface. Now, most of the time between dielectrics, for example, usually the charge density on the surface is zero, because this is the free charges now. And normally there wouldn't be any if you had a boundary between two dielectrics. You could arrange it that way, but normally you don't. So the first boundary condition is that this D normal component is discontinuous by sigma. All right? But we got a second equation here, E. So let's see what the boundary conditions on E would be. So again, we look at our surface. Only this time, we're going to use Stokes' law. We knew that the curl of E dot dA was equal to the line integral of E dot dl going around the box, keeping it to our left. So now we look at our surface, and we'll go around a box like this. We'll go this way, and the integral all the way around the box is going to be 0. But on this face, the dl is arbitrarily small, so you get nothing on this line. You get nothing on this line, because E times the infinitesimal distance. Here you get E going this way. That's the tangential component of E, parallel to the surface, times L. But here, you go the same distance in the opposite direction. And so what you get, if this is 1 and this is 2, here you get E tangential in the 2 times L. And here you go in the other way. E parallel in 1 times L is 0, because this thing is equal to 0 for electrostatics. And that means that E parallel 2 is equal to E parallel 1. And our second boundary condition is that the tangential component is continuous. So the tangential component of E is continuous at a boundary, and the normal component of D is discontinuous by whatever charge density is on the surface. And we can use that to solve a huge variety of problems. Turns out both of those equations will be true on the complete set of Maxwell's equations, even when you have non-static things and you have magnetic fields and so on. Those boundary conditions are still going to be true. We'll prove them again when you have the whole works, but it'll turn out that way. So, as something for you to think about, we're going to switch again this weekend. I'm going to do it tomorrow, and David's going to do it on Friday. So I have another lecture tomorrow. Problem for you to think about, familiar one, the infinite dielectric plane. Dielectric constant kappa. Put a charge Q out here, some distance L in front of the plane, and find the force on the plane. How'd we solve that with when it was a conductor? Images, right? Well, we suspect, because we know that you can get the answer for a conductor by just letting kappa become very, very large, we suspect that we can solve this by images by guessing that there is a charge Q prime back here, a distance L behind the plate. And that we guess that I can choose Q prime in such a way that I can make the field out here for the sum of those two. Now I'm going to need the field in here. Why? Because the boundary conditions are different. They are no longer that D and E have to be 0 inside this thing. Before they had to be 0 inside it, now they don't. So I suspect that maybe I can solve this by doing region 1 with those two charges, and doing region 2 with a different charge here and nothing in here. When I do region 2 over here, I know I can't have anything in here because then it wouldn't satisfy Poisson's equation. But I know that something's going to be changed by the dielectric being there. So I guess I'll probably have to use some different charge out here. Physically, what does that amount to? If it was a conductor, what would the effect of this charge have been in here? Nothing, because you get no field in there. So inside, it must be that this charge isn't what it was before, it's something else, which would go to 0 if it was a conductor, and something probably not quite 0 when it's not a conductor. And we'll do that next time. And to do that, we'll have to use these boundary conditions that we just worked out over there. Okay, see you all tomorrow.